So far, you may have the impression that quantum mechanics always predicts only averages or probability distributions, but that is not the whole story. Quantum mechanics also allows very special states in which an observable has a perfectly definite value. Those are precisely the eigenstates of the corresponding Hermitian operator. And it is the eigenvalue problem for a linear Hermitian operator that we will be discussing in this section. This is a very important turning point in quantum mechanics because many of the central ideas we use later, such as definite measurement outcomes, stationary states, allowed energies, orthogonality of states, and completeness, are all tied to the eigenvalue structure of Hermitian operators. Let's now introduce the idea of a determinant state. Ordinarily, if we prepare an ensemble of identically prepared quantum systems and measure some observable A, we do not necessarily get the same result every time. This is one of the fundamental features of quantum mechanics. Even if the preparation is identical, the outcome of measuring an observable can still show a spread of values. That is the usual indeterminacy of quantum measurement. So now we ask a very natural question. Is it possible to have a state associated with an observable such that every measurement of that observable returns exactly the same value? If the answer is yes, then such a state would be a very special kind of state. It would be a state in which the observable is completely sharp with no statistical spread at all. That special kind of state is called a determinant state for the observable. In other words, a determinant state is a state in which the observable has a definite, unique measurement value. This idea should already sound somewhat familiar. For example, any stationary state is a determinant state of the Hamiltonian. Why is that? Because in a stationary state, the energy is well defined. Every measurement of the total energy gives the same result. So stationary states are special examples of determinate states with the Hamiltonian as the observable. Here we take the infinite potential well as an example. In that system, the normalized stationary state wave functions and the corresponding eigenenergies are shown here. Each of these wave functions corresponds to a definite energy. So if the system is in the state psi 1, every time you measure the energy, you always get E1. Similarly, if the system is in the state psi 2, every time you measure the energy, you always obtain E2. So if the system is in the state psi sub n, every measurement of the energy returns E sub n. There is no spread in the measured energy. That is exactly what we mean by a determinant state of the Hamiltonian. So this slide introduces an important conceptual distinction. A general quantum state usually gives a distribution of possible measurement outcomes, but a determinant state gives one sharp value for the observable under consideration. In the next slide, we will translate this physical idea into a precise mathematical condition. Now let's make the previous idea mathematically precise. If a state is a determinant state of the observable A, then the measurement of A must have no spread at all. In statistical language, that means the variance of A must be zero. So we must have the expression shown here, which means the average of the squared differences between the measured value of the observable A and its sample mean must be zero. In operator notation, the variance of the observable A in the state psi is expressed shown here, where we have used the general expectation value formula to express the expectation value of the square of the derivation of the operator A hat from its average value. Now, if the operator A hat is Hermitian and the expectation value of the observable A is real, then the adjoint of the operator A hat minus the expectation value of the observable A is also Hermitian, as is proved here, where we have applied the three algebraic rules of an adjoint operator. They are the adjoint distributes over sums and differences, conjugation of scalar multiples, and the adjoint of the identity operator equals itself. Please note that the expectation value of the observable A can be expressed as the expectation value of the observable A times the identity operator. So the adjoint of the expectation value of the observable A is equal to the complex conjugate of the expectation value of the observable A times the adjoint of the identity operator. Now, since the deviation operator delta A hat is Hermitian, its square can be expressed as the product of the deviation operator and its adjoint. Next, we define the new Kit vector, which is the deviation operator acting on psi. Its corresponding bra vector is obtained by simply taking its adjoint, as shown here, because the adjoint swaps kits and bras. In arriving at the last expression shown here, we have applied the rule that the adjoint of a product reverses the order, as shown in this expression. So we have the final result as shown here for the bra vector of the new defined Kit vector as shown here, which is the deviation operator acting on psi. Now, since the new Kit vector phi is defined as the deviation operator delta A hat acting on psi, the corresponding bra vector is the adjoint of the Kit vector. We see that the variance of the observable A is the inner product of phi, which is the norm squared of phi, or the norm squared of the deviation operator acting on psi. And because it is norm squared, it must be larger than or equal to 0. Consequently, if we want to have the variance of the observable A be equal to 0, we see that the only way is to have the deviation operator acting on psi be equal to 0. Rearranging terms, we obtain the expression shown here. So we have the operator A hat acting on psi must equal the expectation value of the observable A times psi. So we say that a wave function satisfying this expression, then that wave function is the eigenfunction of the operator A hat. And the corresponding expectation value of the observable A is called the eigenvalue, and it is often denoted by lambda. So this equation is the eigenvalue equation for the operator A hat. So we have reached a very important conclusion. If a state is a determinant state of the observable A, then the corresponding wave function must be an eigenfunction of the operator A hat, and the definite value of the observable is the corresponding eigenvalue. This is one of the most fundamental results in quantum mechanics. It tells us that the physical idea of a sharp measurement outcome is mathematically equivalent to the state being an eigenstate of the operator representing that observable. So let me phrase that again in a simple way. A state has a definite value of an observable A if and only if it satisfies the eigenvalue equation of A hat, the operator A hat, which is the equation shown here. So from now on, whenever we see an equation of the form here, we should immediately interpret it physically. The wave function psi is a state in which the observable associated with the operator A hat has the definite value lambda. On the previous slide, we showed that if a state is determinate, then it must satisfy the eigenvalue equation. Now we show the converse. If a state satisfies the eigenvalue equation, then the observable indeed has a definite value in that state. Suppose the state satisfies the eigenvalue equation shown here. Assume also that the eigenfunction psi sub n is normalized. Then the expectation value of the observable A in this state is given by this expression. Now because psi sub n is an eigenfunction of the operator A hat, we can replace A hat acting on psi sub n by the corresponding eigenvalue lambda sub n times psi sub n. So the integral becomes the expression shown here. Since the state is normalized, the integral of the absolute square of psi sub n over all space is equal to 1. Therefore, the expectation value of the observable A is exactly equal to the eigenvalue. This result completes the logical equivalence. On the previous slide, we showed that a definite state must be an eigenstate. On this slide, we show that an eigenstate indeed gives the corresponding definite eigenvalue. So the two statements go together. Therefore, the eigenvalue lambda sub n is not just a mathematical parameter appearing in a differential equation. It is the actual physical value obtained when the system is in that eigenstate and we measure the observable A. This is why eigenvalue problems are so central in quantum mechanics. They identify the states with sharp measurement values and tell us what those allowed values are.